everyone, and welcome to today's SANS webcast, Evaluating Network Traffic Analysis Systems, Requirements and Challenges, sponsored by Awake Security. My name is Carol Auth of SANS, and I will be moderating today's webcast. Today's featured speakers are Kevin Tolly, founder of the Tolly Group, and David Pearson, Principal Threat Researcher at Awake Security. If during the webcast you have any questions for our presenters, please enter them into the questions window located on the GoToWebinar interface at any time. Please note that this webcast is being recorded, and a copy of the slides and recording of this webcast will be available for viewing later today and can be found on the SANS registration page. And with that, I'd like to hand the webcast over to Kevin.
Thanks, Carol. Thanks, everyone, for joining us today. As Carol noted, my name is Kevin Tolly, and I am the founder of the Tolly Group, and will be presenting today on behalf of my team. Our topic today is network security, more specifically, network detection and response. NDR is a new approach for dealing with threats that would be undetected by traditional IDS, IPS, and related security technology. I will be reviewing testing conducted by Tolly of the Awake security platform that compared it to the Darktrace Enterprise Immune System. Awake provided test scenarios that its customers have identified as relevant. Testing was performed in a live high-tech company's production environment. The project was conducted by Tolly in August 2019 and commissioned by Awake Security. The full results can be found in Tolly Report 219139 and provides a more granular level of detail. That report can be found free of charge on reports.tolly.com and is also available directly from Awake Security. Carol, next slide, please. So against this background, let's see what a few other organizations have noted. Here is why detecting non-malware-based threats is important. According to the FireEye 2018 threat report, 90% of attacks did not contain malware, but used other tactics like social engineering, credential theft, and spear phishing. As this trend continues, the ability to detect malicious intent versus malicious code will become increasingly important. Here's why signal-to-noise ratio that we'll be talking about is important. 79% of security teams surveyed by EMA state that they are overwhelmed by the volume of threat alerts that they receive. Minimizing useless and noisy alerts enables teams to focus on and effectively counter actual threats. Here's why alert validation is important. Cisco's 2017 Security Capabilities Report shows that 72% of security alerts are illegitimate, and the cost of malware containment study by Ponemon estimates the average enterprise spends $1.2 million per year validating the accuracy of their security alerts. Providing the tools to quickly and accurately determine the legitimacy of an alert is key to the overall adoption and success of the solution within organizations. Our test was comprised of 5 different scenarios that exercised different methods of data theft, exfiltration, and credential theft that ran over common protocols and programs such as browsers, DNS, and SMB file protocols. In addition to verifying accuracy of detection, the test noted all alert messages generated during a particular scenario. These were later evaluated for accuracy. Accurate messages were classified as signal, and inaccurate or irrelevant messages as noise, thus allowing engineers to calculate a signal-to-noise ratio, or SNR, referenced above. Next slide, please. So here's a quick look at the solutions that we compared. Current versions as of the test date were used. This graphic, by the way, and all others in my presentation are excerpted from our full report that I referenced a few minutes ago. And today, our process will be that I will lead you through the key parts of the test as shown in our report. And when I finish up, David Pearson of Awake Security will dig down deeper into some of the the elements, threat elements, and some of the secret sauce of the Awake Security solution. Next slide, please. Okay, good. So this will take a few minutes, but this is the crux of the test. While a detailed discussion is beyond the scope of this webinar, please note that the MITRE Corporation has been compiling a global database of threat tactics and techniques for some years now. All of the scenarios in our test were built on techniques documented in their attack knowledge base. I certainly recommend that you research that more on your own if you haven't already. So, threat number one, IoT threat exfiltration. In this test case, 3 similar Raspberry Pi IoT devices performed standard video surveillance tasks. One of the 3 devices is set up to perform a low and slow exfiltration of data to an attacker-controlled site hosted on a common cloud provider. The challenge is to identify these signs of malicious activity from a device that is behaving differently from a similar single-function device on the network. You can see already that this is a vastly different and more complex threat than, say, a malware sample being carried in a document or a SQL injection attack. The second scenario, data theft. In this test, an unregistered Google Chrome browser extension has been configured to gather information on the endpoint's browsing history and cookies and communicate these to an attacker-controlled site hosted on a common cloud provider for both command and control and data exfiltration. Number 3 is focused on data exfiltration specifically. This test uses a common DNS tunneling tool, DNScat 2, to perform tunneling to an external network entity to perform, again, a low and slow transfer of sensitive files outside the organization. Hopefully you're seeing a little commonality here. Low and slow is mentioned twice. What we're seeing is complex attacks that take place over time as opposed to a hit and run, something that happens quickly with particular attack coming in. So a very, very different challenge and a very, very different solution to solve the challenge. So item number 4, test number 4, insider threat. A legitimate but malicious insider uses built-in operating system tools to gather sensitive files from other network devices. The insider connects directly to the IP addresses of other systems using Windows SMB protocol to connect to sensitive administrative shares. The files are then exfiltrated to an attacker-controlled site on a common cloud provider. Again, we're seeing what could look like just regular traffic from our corporate environment to a common cloud provider. You fill in the blanks as to who it is. That looks normal, but isn't normal. And that's the key, and that's the challenge. And then the 5th one here. A vulnerable admin account is compromised via a Kerberos brute force attack. Lateral movement is then initiated by an authenticated RDP session to transfer files back to the malicious system where the data is, again, exfiltrated to an attacker-controlled site on a common cloud provider. Okay, that's an overview of our 5 scenarios that we did. Next slide, please. So we don't have to drill in here. What is important to note is simply that our test environment was built over an actual live customer network that both solutions were monitoring. So NDRs need to be tested in such environments where they can monitor typical traffic and use that as a basis for comparison against possible threats. So here too, again, for many, many years, whether we were testing IPS, IDS, certain next-gen firewalls, we were able to test those quite effectively in an isolated laboratory environment where we simply hit them with samples and see which ones they detected and which ones they let pass. That's not how you do it here. Again, while your environment is going to be different, The purpose of this slide, figure 2 from our report, is just to show you that it's a live environment, a complex network, and that's really what needs to be understood when dealing with NDRs and evaluating NDRs on your own or in conjunction with the vendors. Okay, next slide, please. And metrics too. So here again, when we look at what most of us are used to dealing with, which is the malware-based type of attacks, SQL type of attacks, malicious attacks along those lines, we were usually looking at just detection rates. It caught it, it didn't catch it. Here the metrics are different. We're introducing some new metrics. We're taking a different look at metrics that may sound familiar. So let's see what we have here. So in our case here, we've got a couple of them. Detection accuracy. We measure detection accuracy at its most basic level. So we ask this question: was an alert indicating malicious activity of any sort generated? Okay. This value does not measure the quality or details provided by the system, including identifying the specific attacks launched during the test. Just a kind of a binary. SNR, signal to noise ratio. We mentioned that a few minutes ago. And here too, we talked about being overwhelmed with data, with messages. I've said several times, I'm sure David will say it, but let me say it again. These are low and slow attacks. These are attacks that could be, taking days or more, to run. So with network traffic being potentially thousands of packets a second, it's very easy to just get all kinds of potential alert messages that are not very meaningful or possibly completely meaningless. So understanding the good messages versus the irrelevant messages is very important. So how focused and accurate were the alert messages? Valid alerts, as noted, are classified as signal. That's good. And invalid or irrelevant ones classified as noise or bad info. We want an SNR as close to 100% as we can get. Alert validated. Here we note the ability of the system to display data that clearly supports the direct declaration of malicious intent. So we looked at the binary of detection accuracy, yes or no, but then we look at the validation. What kind of information are we getting that tells us about the event? Why do we care? Because we need to get direction, to get focused on where the problem is happening so we can, if it's a breach or some kind of problem, stop it as quickly as possible. Okay, next slide, please. Okay, so this is a slide, figure 1 from our report. First a high level, then a drill down before I turn things over to David. So in our set of 5 test scenarios, Awake detected 5 attacks to 2 for Darktrace, for 100% versus 40% in that category. Across all 5 scenarios, Awake demonstrated an overall SNR of 95% to 6.6% for Darktrace, and we'll drill down in a minute. The alert validation results mirrored the detection accuracy with 100% and 40% for Awake and Darktrace, respectively. Let's see some details on the next slide. So next slide, please, Carol. Okay, again, a lot to look at here. This is also pulled from our report, so if you want to take a look closely at this, you should get the report. Again, these are long-running attacks. There's lots of data. What we did here was our best to try to distill and consolidate the results. I think we did a pretty good job, but it's still a lot to look at. So Awake will go into some of the visual benefits of their platform shortly, but let me use my time to compare the results of the 2 tests. I note first, though, that in 2 of the attacks that were undetected by Darktrace, there were over 30 Dropbox activity alerts that were generated that were unrelated to the attack in progress and thus classified as noisy alerts. Both systems detected attack 4, the insider threat. Awake had no noisy alerts, where Darktrace, here too, generated a dozen noisy Dropbox activity alerts. Awake validated the attack by showing users connecting to administrative shares, those are the dollar shares, shares prefixed with a dollar sign, and downloading files. Darktrace validated the attack by showing a record of a large number of unsuccessful logins. Both systems also detected attack 5, credential theft via brute force. Again, Darktrace generated a dozen noisy Dropbox alerts. Awake generated a single noisy compliance alert. Awake validated the attack by showing numerous failed logins, followed by a successful login and RDP capture. Darktrace validated the attack by showing a record of a large number of failed attempts over a short time. With number 5, credential theft. Oops, hold on. Okay. And that's all I have to say on that. Okay, so that's a summary of what's going on. I'm going to give you a quick recap slide before I hand things over to David. So if we can have my last slide, please. So just to recap, everything you've seen me discuss, every visual you've seen me show here comes from the report that you see before you now, Doc 219139. You can get it free of charge from Tolly Group and from Awake Security. It will give you a lot more information than we're able to do in this section, but hopefully it gave you a good start. So with that, let me turn things over to David Pearson from Awake. David?
Thanks, Kevin. Really appreciate it, and thanks for going through quite detailed there. So my name's David, Principal Threat Researcher at Awake Security, and I'll talk through a little bit more about the test and some of the things that we have identified as requirements that are important and challenges that we've faced. In a day-to-day kind of perspective, I get the opportunity to really work with the platform and the product that we've created to provide value to our customers, whether that's through validating different things that we've identified in networks, or if that's providing additional capabilities on top of that, such as hunting and incident response kinds of things, as well as simply identifying what are the challenges that we have to face that are going forward. So I get a really good opportunity to work hands-on with the system and with customers, and also think about what's coming down in the future. Next slide. All right, so for NTA solutions, and I don't really want to talk a whole lot about Awake specifically here. I want to talk about the category itself, but maybe a couple of little Awake things will come out. But I wanted to point out that there are a few requirements, the way I see it, for these kinds of solutions. And the first one is breadth of detection. Kevin earlier in his slides and as he was speaking was talking about different reports that have anywhere from 50 to 90% of their research they essentially have found don't involve malware anymore, right? So it's literally just living off the land. It's other types of techniques that don't have to do with the viruses and other sorts of malware that were common in the heyday of security. It's not really that game anymore. There's just so many different ways to hide within legitimate programs, essentially. And so being able to identify things that are both malicious in terms of malware and also malicious behaviorally is really, really important. Signal to noise, similar to how Kevin was describing this, it's really important to be able to identify when something actually matters. If you think about anomaly detection and you think about networks that have sometimes gigabits of traffic per second, there's just so much that can be anomalous, right? So finding the things that actually matter out of there, whether it's through anomaly detection or if it's through behavioral analysis or some ensemble approach that kind of mixes those and other things together, you really need to be able to find the things that actually provide the most valuable signal to the end user. Finally, the quality of the alerts themselves. So I want to ask you to step outside of security for a second and think about maybe the law enforcement and going to a crime scene. And if you're an investigator and you walk into a crime scene, what are the kinds of things that you want to ask yourself, right? You'll be asking essentially the 5 W's if you go way back to kindergarten, right? Who, what, when, where, why. Those are the questions that you really want to be able to answer. Those questions give you the information that you need to contextually enrich your understanding of the situation and identify, the answers to those questions, but also what should I do next? What's the key for my next step? And that's something that NTA can provide here. Next slide. Now going back to the environment itself, so Kevin described quite a bit about how we were in an environment that was a high-tech, real environment, and we overlaid our setup there as well. So there were quite a few different real devices that we had created, and I say real intentionally because with previous types of technologies, it was relatively simple to do testing, right? You didn't need to have this entire background. You didn't need to have realistic behaviors over time. It was simple enough to be able to show that something in a binary way did or didn't detect something, right? But that's not true when you have systems that take in all of this context, the 5 W's that I just talked about. You can't simply replay traffic, or you can't simply download a whole bunch of malicious executables. That tests such a small amount of what's actually meaningful, and in some respects, the systems will actually be smart enough to say, hey, I know that that's fake traffic. So the key here is being able to identify and create real environments where we have real users with real behaviors that are really related to actual jobs that they might be doing in the real world. So that's something that's definitely hard to fake at scale. But this is, it's a requirement to really build something that's more meaningful here. Next slide. So we talked about this a little bit previously, but wanted to drill a little bit deeper. When we were deciding what kinds of things to do to make this the most compelling and meaningful test possible, we did our homework. We reached out to all of our customers. We worked with Tolly Group. We surveyed what other threat research teams across network, endpoint, and so on were doing. What were the things that they were discovering, and why does that matter, right? And we put all of those things together into these 5 different use cases that Kevin had described earlier, and really drive home the importance of being able to cover a wide variety of use cases that are really based on modern and in some cases low and slow attacks. So we've got a few different kinds of attacks here, right? We had one that was more or less malware. We have 2 that spanned multiple attack stages, and attack in this sense I'm framing with respect to the MITRE ATT&CK framework. So we leveraged that quite a bit to categorize what we created, so that it was very clear in a language that anybody from any part of security could understand. And then finally, there were a few attacks that were focused on just a single stage, but not a single event. It was still something that evolved over time, which is a little bit more complicated than traditional things. And we'll dig into the details here as we go into the next slide. So first one, IoT threats. I think it's pretty obvious. I'm sure most people have a smart speaker at home or maybe at work, and there's tons of different smart light bulbs and smart toasters and all sorts of crazy things. There's just so much smart technology that are on networks, whether it's your personal networks or it's your corporate networks. And it really is a problem, right? That none of these devices have ways to really manage them. They're very, very easy to sneak in right? And so it causes problems that are very difficult to solve with endpoint technologies or other technologies. But what happened here was we had these 3 Raspberry Pi devices, and so having the ability to identify the fact that these devices are similar, right? To be able to say that there are 3 devices on this network that have been. Sorry, guys, I've got a dog walking past my window. Anyway, so if you can communicate the fact that these 3 different devices are doing essentially the same job, right? Kevin mentioned they were communicating, and I think they were streaming video, right? If you can identify that they're doing the same thing, but one is doing something just a little special, that's really intriguing. And being able to find that doesn't really work with standard anomaly detection, things like that. You need to leverage more complicated capabilities. And this was actually the reason why we decided to do to model something like this. In addition, was we actually had a customer that we worked with where we essentially did this. They had a rogue. We found out later they had a rogue IT admin who installed surveillance software on just a few of the mobile devices that were deployed within the network. And this was a network of thousands, if not tens of thousands of devices. And by using the similarity analysis, we were able to find just a handful that had this special thing. And that was the key to solving a problem that they didn't even know they had, but was definitely a big security issue. Next slide. All right, so man in the browser, we recognize this as a trend that's definitely picked up steam, especially in the last year. I've been to a few conferences where people have talked specifically about man in the browser, and as we've been investigating different things with our customers, we've noticed quite a bit of behavior going to the browser, and it's a perfect place, right? Because everybody has a browser that's a user, and so much of today's business happens in the browser. Your credentials are there. Sometimes your password manager is there. You've got all these different things that are really great targets for somebody to take. And so this was something that we felt to be a really compelling use case that really pointed out the importance of being able to detect this. And I wanted to tie back into the cloud environment, right? So the way this test was set up, it was leveraging a public cloud provider, because these sorts of cloud providers are so easy to use, and even more so, traditional techniques, you have a domain or an IP address you can do reputation analysis on, but that doesn't necessarily exist when you move to the cloud, right? If you're using Amazon AWS or Google Cloud or Azure, or name your cloud provider, you're using essentially a subdomain of that site, and reputation services don't really exist for that. That's not really something that you can do, and it's not okay to just say we're not going to look at that. It's really a critical part of understanding security as we go into 2020 here, in being able to identify threats that are coming or going to the cloud. Next slide. All right, so third test case, DNScat. This was the one that was the closest to malware. There might be people on the call that would say that it's not technically malware, and I generally agree. But the point is, it's a purpose-built tool that is meant to evade detection, and in this case, to tunnel over a common protocol, DNS. And so it's the closest thing that we decided was relevant to test in terms of malware. And so the way DNScat works by default, it communicates with, I believe it's the prefix DNScat dot whatever you're going to exfil, that's usually encrypted, and it goes to wherever. And so you could surmise that it's possible to simply create a detection that does a regular expression or a string match and looks for that thing. And so you can do that, and that's fine for very basic things. But the problem is the attacker, if they really want to be able to bypass you, they'll also modify that binary. And this is something that's relatively simple. If you think about David Bianco and the Pyramid of Pain, you know, strings and sorts of artifacts like that are really easy to kind of get past. And if you're only detecting that, you're really not making it hard for the attacker, right? So being able to identify the behavior itself is so much more meaningful. And this test actually there was a creation of this alternative version of DNScat so that we could test both the standard DNScat and this more complex DNScat. And so it's important to recognize that you shouldn't just look at tools themselves, right? You should think about the behavior and try to characterize and profile it across the entire realm of possibilities. Next slide. Okay, so insider threat, generally speaking, really notoriously hard to detect, right? The thing that we were testing here, as Kevin mentioned, right, there was a behavior that was happening. It was scripted. The user was reaching out to a bunch of different admin shares, and it was in a kind of a common recurrence, right? It happened once a day, and over time the information was collected and then later exfiltrated. So it's important to be able to identify and discern the differences between what's common within the network and what's something that looks a little bit off. In this case, scripting this behavior is one thing that kind of catches your eye, right? Sometimes admins will script things, but collecting a whole bunch of different files from different privileged shares of other systems within the network and doing that in a way that's directly to their IP addresses instead of enumerating their names, just a little bit weird, right? It doesn't quite compute. And then of course being able to tie that together to the exfiltration itself, right? Connecting those dots, that's really critical. Next slide. So the final use case here, 5, this was the most challenging one, and this was meant to show exactly what it's like when an attacker essentially goes through the full attack lifecycle. So we did assume that the attacker was on the network, but that was all we assumed. They had gotten onto the network, but the Kerberos brute force, remember that was the first step, that brute force was successful, and that successful brute force compromised the admin credentials. Those admin credentials were then used to RDP, so common tool that's built into all Windows systems, RDP to another system, collect data from that system, download it back to where they were, and then at some point later, sometime across the days, get that information out to an attacker-controlled location. And so if you think about the brute force part of that, right, it's really easy with anomaly detection and all sorts of pretty standard techniques to be able to detect that. So no surprise there, pretty easy to detect. But being able to also identify that not only was it detected, but it was successful. There was a successful brute force attack. That gets a little bit more complicated, right? You have to think about what that means. From there, being able to identify the communication that happens after that, after the successful compromise, being able to connect the lateral movement and the collection of data followed by exfiltration. When you have all of those different steps and you can wrap them together and build context around them and show that they all started from that single brute force attack, that's when you really provide the value to the end user. Next slide. So in summary, right, there's a few things that I wanted to point out here. It's really much more complicated to test these sorts of solutions, but it's necessary to create this much more rich and complete environment to test them. Otherwise, you're essentially not actually getting to the crux of what they can provide you. And it's fine to detect malware, but you need to detect more than that, and you need to detect things that happen over time. You can't simply always alert on the first sign of something that may be interesting, because there's a lot of anomalies on the network that are absolutely not interesting. And to waste somebody's time on that ends up, first of all, burning them out, but also occluding their view into something that's much more important. And going back to that fifth use case, if you can wrap things up in a nice little package and identify exactly what's going on across multiple steps, that's something that provides so much value to your end user. And the more situations that you can provide that go toward that, the better. So with that, I'm all finished and open things up to questions. And Carol, please go ahead and take it back over.
All right, yes, thanks for that great presentation. We have some questions ready for the Q&A. However, if anyone has a question for our presenters, please enter it into the questions window now. Our first one is, are there any benefits to having both endpoint and network behavioral analysis?
Yeah, so absolutely, right? If you think about some of the things that you can see on the endpoint and some of the things that you can see on the network, there are overlaps, of course, right? You'll both be able to see things that are looking at lateral movement. You'll be able to see different things. You'll be able to learn more about them with different solutions. They'll complement each other a lot in some of those middle kinds of situations. But if I want to, for example, understand the registry keys of a system and see if anything was installed to run on startup, that might not be something that I can do from the network. So being able to leverage some of this information and pull it back in is really important. And it goes both ways. I think there's quite a complementary relationship there. Absolutely something that would be beneficial from both sides, having both of those technologies.
Yep, and Carol, this is Kevin. From my 2 cents, I agree with David. We're talking here about new threats, but it doesn't imply that old threats go away, right? They're all still there. I think we should just make sure everybody understands that the assumption is, there's still going to be malware. There's still going to be things there. There's other devices like CASB solutions or whatever that even augment the traditional endpoint security solutions. I think anybody who's involved in security would agree that it's multi-tiered, multifaceted. You want to get all the help you can get. David?
Absolutely, I agree with your points. It's more of a team sport, I guess you could say.
Yep,
right?
Exactly. Carol?
All right, thank you. Why is background traffic so important?
So this is Kevin. Let me take that first. So, David addressed it in his presentation, but it's worth repeating. You need to have a real environment in order to evaluate devices. It's not something you can evaluate any longer in a lab environment where you throw a sample through or you have a particular signature, right? We didn't really use that term a lot, but that's used a lot in the past. There's a signature for the attack. What David brought out, which I thought was really interesting, is what we're seeing now with the more sophisticated attacks is that there is no signature. The signature is something different. So it's not a typical thing where we can load in the new signature database and say, aha, I see you trying to slip that past me, I gotcha. David's example was really, really good, where he says, okay, we've got a couple of these devices, we monitor them, we get to learn what their normal behavior is, and then we see one of them or a few of them behaving differently, perhaps sending different size packets, sending a little bit more data or contacting an endpoint that the other ones out on the network that other ones don't do. So that's all essential. So you can't really test those types of things with artificial traffic, which is another type of background traffic. And as I brought up in my presentation with this whole signal to noise ratio, is what we used to call false positives, right? With more traditional malware, having a system that just keeps hitting the alert button saying, "Oh, could be something, could be something, could be something," is a very expensive proposition because your security team has to track something down, which could not be worth tracking down. So by having background traffic, that also puts pressure on the NTA, the NDR solution, to make sure that it's not detecting and reporting things that it shouldn't detect. David, did I leave anything out there?
No, the only other thing, the way that I like to think about these technologies is if you think back to the first chatbots, right? You could very clearly tell that they were just scripted, right? There was something just patently fake about them, right? You knew exactly, you could almost do an Oracle test and you could know exactly what they were going to say based on your input. And if you go to good chatbots today that are leveraging state-of-the-art machine learning and artificial intelligence, and as you get to the point where things get closer and closer to the Turing test, it's much harder to be able to tell when something's fake, right? You're essentially what I'm trying to describe is a similar direction where our technologies need to be tested better by more complete and more realistic versions of the things that they were before in order to really understand if it's truly doing the job.
Yep.
All right, thanks. Why not prevent every attack instead of taking a detect and respond approach?
Yeah, so can you say that again? Why not? Sorry, what was that?
It's why not prevent every attack instead of taking a detect and respond approach?
Thank you. Yeah, so I think this goes a little bit similarly to what we were just talking about, right? If you think about these attacks that are possibly low and slow, or that do essentially the same things that other systems in the network do, right? If you simply alert at the first time, or if you try to prevent, right? Being able to do that, if you're preventing, you may actually be stopping business justified activity that will cost you money in a different way. But if you're alerting, you're essentially burying your sock in a bunch of stuff that they may or may not understand, may not have the context, don't know if it's important, and so on and so forth. So it's important to alert as quickly as you can in a confident manner, but understand that it's not, I don't want to say often, but it's many times the case that you need to have more of this information that evolves over time. And time may not be days or weeks, right? It might be minutes. It might be a couple of hours. There are different ideas of time that help to get you to the confidence that you really need to address something as definitely a problem.
Yeah, and everything's a trade-off too, right? If you look back at prior generation firewalls, IPSs, things like that, you can do all kinds of wonderful inspections, deep packet inspection, but if the hardware wasn't up to snuff, it could slow down your user sessions. I remember at one point there were some firewalls that said, we're going to be really, really secure. Our default is to have every port blocked. Well, that's great, but as David pointed out, you still have to be able to do business, and people couldn't do business, and it would be such an effort just to try to open up ports that it really wasn't a good balance. I think in many things it always comes back to a balance, right? We're protecting the organization, protecting the business, but we have to let the business run too. David, would you agree with that?
Oh, totally, absolutely.
Yeah. So good. Carol, anything else for us?
Yeah. Do these types of systems do away with the need for a large SOC team?
No.
No.
So for those of you who are on the call and are worried about your job, I have good news for you that I believe your job will get more interesting, right? So a lot of the things that we're able to automate with this context is just all of the I don't want to say menial tasks, but the stuff that you don't want to do, right? All of the hunting down and talking with the NOC and trying to understand with IT, depending on what your organization looks like, trying to get all of that information, we're just providing that to you so you can actually do your job better, right? You're able to do the things that you're really good at more quickly, focus more on them, and to really provide more value to the business. So I'd say, we're in that respect, we're just making your jobs more interesting, but also recognizing that we really do have a shortage of SOC analysts and security professionals in general in the field. So we're trying to give the folks that we do have as much power as they possibly can to help defend networks today.
Right, and by having a good signal to noise ratio, you eliminate a lot of busy work chasing down problems that aren't really problems, right, David? I mean, that's key. Just eliminate a lot of junk.
Yeah, we absolutely.
Yep. Good.
All right, I think we have time for one last question. My SIM already provides the information you talk about. Why do we need to add an NTA system?
David?
So SIMs, in some respects, they do provide this beautiful view of everything, right? The single pane of glass. But one thing that you need to, of course, be understanding of is SIMs are only as powerful as whatever is underneath them, for starters, right? So being able to have value from the systems that are underneath them is the first critical thing. But second is being able to take that information that, if you're using your SIM, and correlate it and to draw conclusions from it and to do really contextual things. You might have all that data, you might have this big mound of information that does contain the information that you care about, but actually getting the value out of it that points out these things isn't necessarily a strength of the SIM. Whereas for an NTA solution, right, we're trying to solve those 5 W's. We're trying to provide that value to you directly.
Right, they're complementary. They do different things.
Absolutely.
Yep.
All right, well, that concludes our webcast. Thank you so much, Kevin and David, for your great presentation.
Sure.
And to Awake Security for sponsoring this webcast, which helps bring this content to the SANS community. To our audience, we greatly appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, including this one, please visit sans.org/webcasts. Until next time, take care, and we hope to have you back again for the next SANS webcast.